Hey, welcome to this tutorial on solving linear equations. We will look in this lecture at three perspectives to solving a linear equation. So before we move further, let me pause for a moment and you should think about how we might solve this equation. 2x minus y equal to 0 and minus x plus 2y equal to 3. Okay, so there are three ways in which this can be solved. The first is a row view, which is the most common way of solving a system of linear equations. The second is a matrix view, which is what all modern computing systems use to solve linear equations. And note that this method is most valuable when the number of equations and the number of variables goes up. The third is a column view, where essentially you are looking at columns, that is the columns of x and the columns of y, and then taking a vector view to the solution. So let's start with the row view. In the row view, what you are essentially doing is you look at the equation 2x minus y equal to 0 minus x plus 2y equal to 3 independently of each other, and then you plot it on the Cartesian coordinate system. And once you plot it, if the system of equations has a solution, those lines will converge, and the point of convergence would be your solution. Here it is. The yellow line represents 2x minus y equal to 0 for you, and minus x plus 2y equal to 3 represents the red line, represents the second equation. The point of convergence is here, and this is your solution here, 1, 2. So as you would note, when you have a linear equation system with two variables, the solution would be a point. Now tell me, for a three variable system, how would the solution system look like? Well, that will be a plane. Okay, let's move further. The second view, as we said, is the matrix view, and this is how we would represent the system of equations. What you see here is this is what you call the coefficient matrix. This is of course the column variable vector, and this is your constant. So in the matrix view, what you would essentially do is you will look at this first, then you would combine that with this, and then you try to reduce this equation set in a systematic manner, coming down each step to arrive at the solution. So let me take you through these workings, because it is, at least on first look, it's certainly not intuitive, but once you get a hang of it, you will see how effective and beautiful this equation process is. So what you do first is you look at the line 2 minus 1 0. So 2 is the coefficient of x, minus 1 is the coefficient of y, and 0 is your constant in the first equation. Similarly, second one you have minus 1, 2 and 3. Now in any system of equations, so long as you are operating on the left side and the right side equivalently, there is no change to the system. 2 minus 1 0, thus suppose you divide that by 2, you get 1, minus 1 by 2 and 0. So why do you divide it by 2? That's because here this is what you call the first pivot, and when you pivot this, if you want to get 1 here without changing the system, you have to precisely divide it by 2. So you divide this by 2, you get 1, this is minus 1 by 2, and 0 remains 0. And in this step, the second equation that remains untouched. Now the second rule that you should know is if you add or subtract one system of equations from the other, so long as you're doing it on both sides, there is again no change to the system of equations. So in this case, what we want to do is we want to bring this down. This we want to get it down to 0. So you just add 1 to minus 1, you get 0 here. Similarly, when you add minus 1 by 2, you get 3 by 2, and 0 plus 3 of course is 3. So as you move from step 1 to step 2, or rather from on the second iteration of this matrix, you essentially have reduced column 1 as 1, 0, minus 1 by 2, 3 by 2, and this is 0, 3. Now here what you're going to do is you want to bring this number down to the identity condition. So therefore you would divide this throughout by 3 by 2. So you get here 0, 0 remains as 0, 0 divided by 2 by 3 is 0. Then 3 by 2 divided by 3 by 2 is 1. And 3 divided by 3 by 2 is 2. So 0 divided by 3 by 2 is 0. 3 by 2 divided by 3 by 2 is 1. 3 divided by 3 by 2 is 2. As you can see, as you have moved down from this matrix, from the original coefficient matrix, you have come down to what is called the lower triangular form of the matrix. So you have 1 here, 1 here. The diagonals are all 1. Whatever is left to the diagonal is 0. And to the right of it, you have a very simple set of numbers. Now from here, you recreate your equation set. You get 0x plus y equal to 2. That is your lower line. The upper line is x minus 1 by 2y, which is 0. So you have y equal to 2 and x equal to 1, which is of course the same thing that you have here. Now you note on the matrix view that really what this becomes very valuable, as I said, as the number of equations, the number of variables goes up. So when you're moving, so now this is on the 2-degree plane. Now if you go to the 3-degree plane, 4-degree plane, or maybe the 8-degree plane, you have 8 equations and consequently 8 variables, and therefore probably the matrix view probably is the only way you can solve a system of linear equations. And this is what, as I said, all modern computation packages make use of this for solving simultaneous linear equations. So row view, to summarize, yes, it's very straightforward, but it has limited utility because as the system of equations becomes more and more complex, it becomes very tedious to use this. While the matrix view, it's very amenable to scalability in terms of the dimensions. Now, third perspective we have is a column view. So here, what you're really doing is you would look at, instead of the row wise, you would look this column wise. So the first column is 2x and x. You place that here, 2 minus 1 into x plus minus 1 comma 2 y equal to 0, 3. Now these are what you would call singular column vectors. So therefore, when the way to interpret a system of equations would be that a linear equation system is nothing but a linear hybrid combination of columns. So the problem then essentially boils down to how should you combine, in what parts should you combine these two column vectors in order to arrive at 0, 3. Let me repeat that. In what parts should you combine the two column vectors which you have here in order to arrive at 0, 3? Now, in this case, we know, of course, that x equal to 1 and y equal to 2, and therefore what we would do is we will draw this out using column algebra, column like vector geometry, and this is what you get. This is basically nothing but the vector interpretation using concepts in geometry and algebra. So what you get here is this is your 2 comma minus 1 vector. You take one part of that, x equal to 1, then you add, and this vector that you have here, this is minus 1 comma 2, this is the column vector for y, and therefore when you, how do you add vectors? You take this vector, then you create a parallelogram of this vector on at this pivot, and then 2 times this. Why 2 times? Because y equal to 2, and you would see that what you get here, what you arrive at, is exactly 0, 3. So this is extremely intuitive once you've seen it, because this immediately helps you to understand how the algebra of linear equations is related to vector geometry, and and from there on to subspaces, spaces, and other complex spatial concepts. So um, so that's it for today. So to summarize, a system of linear equations, you can look at it at least from 3 different perspectives. One is the row view, the matrix view, and the column view. Row view is essentially for simple linear equation systems. Matrix view is for complex systems, and column view is really what helps you to really get an appreciation of how this works out at the spatial level. I mean, what really all this means in terms of spaces, and why is it that a system of linear equations is so very valuable when you are thinking in terms of space and when you are really trying to define and describe space, because this has all sorts of applications in complex physics and in various other branches of mathematics. Thank you.